Let me start the recording.
All right, sounds good. Sorry, I'm moving your faces to the side so I can see everyone. If anyone has questions. All right. Yes, today I will be talking about how we can learn about dark matter using strong gravitational lensing. And here is an image on the right hand side. You can also see my cursor, right? That is great. Okay. So this is an image taken by Hubble Space Telescope, which everyone can find on MAST archive, which is publicly available archive. It's the cosmic horseshoe image, one of the most famous gravitational lensing images. The blue that you see is a background galaxy, and the yellow that you see is a foreground galaxy, bending the light of this background galaxy and making it appear really warped and bent into an arc. And this is how generally gravitational lenses that I work on look like. And the work that I'll be talking about today are you can find the details of the work that I'll be talking about in these archive papers that me and my group, the core work in this group that I'm part of, we worked on over the past 2 years. Okay, so let's go over the title of my talk. I'll be first talking about dark matter, what is it, and cosmologically why is it relevant, and then I'll give some introduction on the mathematics of gravitational lensing and how it allows us to study dark matter. And then I will go into more details on what particular properties of dark matter we can probe using gravitational lensing. Okay, let's first talk about dark matter. In the universe, we have found out over the past century, this was a slow revelation. The visible matter that we see in the universe when we look at the sky, the stars, galaxies, quasars, all the baryons that are part of the standard model that emit light, all the electrons, all the photons, only consist of 1/5 of the source of gravity that we observe in the universe. So there's 5 times more gravity that pulls stars together, galaxies together, clusters together. So the evidence for this extra source of gravity, which we name dark matter, comes from various different places. So currently there are very few people who doubt the existence of dark matter. It's an established truth. We have these galaxy rotation curves. So when you observe stars in a galaxy orbiting the center of a galaxy, and you plot their rotation velocity as a function of distance to the center of the galaxy, the prediction from only the luminous component of the galaxy does not match the observed rotation curves, rotation velocities, meaning that the stars are orbiting the galaxy faster and faster as you move away from the center. Meanwhile, we expect from the luminous matter distribution that this velocity to drop as this radius increases. So this tells us that there is extra gravity that is there, that is much bigger than the visible size of the galaxy, which we name dark matter halo. So that when you look at a galaxy, the visible part only consists of 1/10 of the total matter in a given galaxy. The rest is the dark matter halo, roughly 90%. It's much bigger, roughly 10 times bigger in size than what you see with your telescopes. Another really important evidence comes from the cosmic microwave background. This is the light that we observe from the very earliest moments of the universe, roughly 400,000 years after the Big Bang. And this is the light that is emitted from there. It traverses the entire universe and reaches us today. And it covers the entire sky except for some galactic regions that we have to mask. And this cosmic microwave background, which you see in this image, has a certain statistical signature. So if you look at these clumps, if you calculate more precisely the two-point correlation function of these temperature fluctuations that we observe from cosmic microwave background, we find out evidence that in the early universe there was dark matter that caused these acoustic peaks that we observe in this. Essentially, what you're observing is an imprint of the sound waves in the early universe, and these sound waves are influenced by dark matter, and the evidence for that we can see. If there are questions, I can go into more details of how that works. And another important piece of evidence is structure formation today. So if you allow the universe to run its course and form structures without any dark matter, you find out that in 13.7 billion years, which is the age of the universe, 13.8, there isn't enough time to form as many galaxies as we see today in the sky. So you need some seeds, you need some extra mechanism to form the structure, which I'll go into a little more into detail later. So all these evidences are really strong evidences that there is this extra matter component in the universe that exists. And we know that it behaves like matter because as the universe expands, it dilutes in its energy with 1 over the size of the universe cubed, which is what we expect from regular matter. But the problem is, so far, all these evidences for dark matter comes from astrophysical observations. There is no direct detection yet in any lab. And I worked on direct detection methods in my undergrad, and I worked in a dark matter detection lab. And then I was more involved in that search. So over the past 3 years, I shifted into more astrophysical observations of that. By the way, I can answer questions as we go. There seems to be 2 questions.
Yeah, there are 2 questions, and you can answer them now if you want.
What was the year galaxy rotation curve diagrams were observed? I don't remember the exact year, but I think it was around 1960s, 1970s by Vera Rubin. This observation was made. And now Vera Rubin's name is given to a telescope to honor her work. So we have known about dark matter for a very long time. If the universe is vacuum, how did acoustic waves propagate? The early universe was not that much of a vacuum. It was actually plasma. It was hot, dense gas, mostly consists of hydrogen and helium and free electrons because it's really hot. And in that dense plasma, acoustic waves propagate. Okay. All right. So let's talk about a little bit dark matter and structure formation. So what happens is, this is a very rough schematic. It shows the space in 1 dimensions, and the y-axis is density. In the very early universe, 1 second after the Big Bang, everything is roughly homogeneous. The density fluctuations in the early universe is roughly 1 in 100,000. So it's even at the time of this cosmic microwave background, which is much later. So in the earlier universe, those density fluctuations are even smaller. It's 10 to the minus 10, 10 to the minus 20, the earlier you go. So it's very homogeneous, both dark matter and normal matter. What happens is, because dark matter interacts with itself and normal matter very weakly, we know this. Dark matter, because we haven't observed it yet in any experiment, and it's not part of the standard model, it has to interact very weakly. Because of this, it starts collapsing under its gravity and starts forming structures earlier than normal matter, because normal matter is it's plasma, so it's being supported by its pressure, its radiation pressure. So it's unable to collapse while regular matter is collapsing, while dark matter is collapsing. And then dark matter forms these clumps and forms these structures. What happens is, as the universe evolves and expands and cools, the normal matter goes from plasma to neutral. And once that's called recombination. Once that happens, all that support that came from radiation just suddenly ceases, because radiation stops interacting with matter anymore, because it went from being plasma, which is very opaque, to being neutral hydrogen and helium almost instantly, very quickly, considering cosmological times. So then regular matter, it was uniform before recombination, now starts collapsing onto the structures that were formed by dark matter earlier. So this is the important step that we need to have in order to explain the structure formation that we have today. Without this mechanism, regular matter simply doesn't have enough time to collapse into big structures. Okay. Yes. So what can we learn from dark matter? What can we learn about dark matter by looking at these structures that form? So an important quantity that we look at is called the halo mass function. It tells you the number of objects, these halos, these clumps that formed earlier. Each of these is a clump, right? So the number of halos per mass, per halo mass, per unit volume. In this case, this is per unit area in the sky that you observe, but in cosmological simulations, you consider per unit volume of the simulation. So this is what, that's what halo mass functions. It tells you the number of objects per unit mass, per unit volume. So in cold dark matter scenario, which means that dark matter particles are really heavy, so that they are cold today and throughout cosmic history. They move very slowly because they're really heavy particles. Even though that they are born in the early universe, they become non-relativistic very early, very quickly. In that scenario, you can calculate, you can theoretically calculate what mass function you predict, halo mass function. And it turns out it's a simple power law, which you see in this black line. But there are other dark matter models that can also be true. We can live in this cold dark matter universe, and so far this is consistent with evidence. So far, for all the experiments that were run and all the tests that were done, cold dark matter passed those tests, so it's consistent with what we observe. But there are other scenarios that can also be true. Mainly, dark matter can have self-interactions, which do not clearly appear in this halo mass function. But another way that dark matter models can differ from cold dark matter is warm dark matter, which allows dark matter particle mass to be a little bit lower than what cold dark matter predicts, what cold dark matter assumes. In that scenario, dark matter becomes non-relativistic at a later time. Because of that, at early universe, because dark matter was still relativistic, it erases structure below certain scales due to dark matter particles free streaming. They're moving away from those dense points because of their velocity, their temperature. So because of that, you start seeing some suppression below some mass scale, depending on what dark matter particle mass is. But this is under this simple scenario where dark matter consists of only a single particle, single type of particle. You can complicate these. There are hundreds, thousands of different dark matter models. But the general picture roughly looks like this. If warm dark matter is true, depending on this half mode mass, which tells you where this transition happens, you start seeing a suppression in the number of structures that you would normally expect from cold dark. Any questions about this? Let me show you pictorially how this looks like. In a dark matter particle simulation, on the left-hand side, what you see is what you expect from cold dark matter. You see halos and subhalos, which are satellites of bigger halos, at all scales down to the scales that you can no longer observe. But in warm dark matter, you see below a certain scale, you still see the larger subhalos and the bigger halos still forming under warm dark matter. But below a certain scale, the number of smaller subhalos are suppressed.
Can I ask you a question?
Yes.
You mentioned that there is an interaction, or at least you conjecture an interaction between the dark matter formations and then observables from, let's call it like real matter that you observe in the universe from Earth, right? Now,
yes.
What are the, like, in order to know these mechanisms, don't you have to assume what is the nature of dark matter, in which case you can surmise what are the interactions? Are they like strong nuclear interactions, electromagnetic, what have you? Don't you need to make an assumption of what is the content of dark matter in terms of real matter in order to make assumptions about these interaction mechanisms?
Short answer, yes. But in general, what you can do is you can assume this basic scenario, which is cold dark matter. You basically assume in the cold dark matter scenario that there is no interaction between dark matter particles and regular matter. You basically make them completely decoupled. And you also make them decoupled to themselves. Your cold dark matter doesn't interact with itself either. And you make them, the particles, heavy enough such that they're non-relativistic. When you run simulations assuming these things, the observables that you get so far are consistent with cosmological and astrophysical observations. On top of that, you can complicate these, and people have done so, and people are doing so, such as there are various self-interacting dark matter theories. You can assume it can be weak force, strong nuclear force. It can have angular dependence in the scattering matrix. It can have no angular dependence. You can test all these things, but so far, our observation capabilities aren't strong enough to pinpoint what is the case. We don't even know whether we live in cold dark matter or some self-interacting or warm dark matter scenario. So we are at a much earlier stage. Once we confirm which direction to follow, then we'll be able to make more detailed studies.
So basically, you don't make assumptions about what dark matter is, but you do make assumptions on what are its effects.
Exactly.
I see. All right. Thank you.
Okay. So here's the rough picture. So the numbers of these structures, these halos and subhalos, aren't the only observable we have. Another observable is the result of dark matter self-interactions. So when you make dark matter interact with itself, albeit very weakly, but still, let's say it interacts with itself a little bit. And here are the scattering cross sections. What you observe is you see this core formation. So what is this? In the language, in the lingo of structure formation, a cusp is this divergent density profile as radius goes to 0, which is what you expect from cold dark matter. When you make dark matter interactionless with itself, it forms these cusps in simulations. Again, in simulations, if you allow dark matter to interact with itself with varying cross sections, it forms larger and larger cores, the larger the interaction cross section. And these cores are constant density regions within a certain radius. And this is another observable that we see. Once you look at these objects, if you are able to measure their density profile, it tells you about dark matter self-interactions. So that's another property of these objects that can grow. So now, at galaxy scale, so at scales of 10 to the 11, 10 to the 12 solar masses, are galactic scale. So this plot that you see is a really beautiful plot. I love showing this. On the x-axis, you see the halo mass, which is the total mass of a galaxy plus its dark matter halo, the entire object. On the y-axis, you see the stellar mass, which is the luminous mass, divided by the total halo mass in logarithmic scale. So there is in galactic ranges, it's the galactic mass scales, 10 to the 11, 10 to the 12 solar masses. It turns out star formation is the most efficient. If you go heavier to cluster scales, what happens is there are these active galactic nuclei, which are active supermassive black holes that blow material out of these potential pits that suppress star formation. So you get less efficiency. On the other hand, if you go to lower masses below galactic scale, so this is sub-galactic, dwarf galaxies, anything lower, again, star formation is very inefficient because of stars themselves. So the stars that form, the early stars that form in these objects, blow the rest of the gas outside of the object to intergalactic medium. So no more star formation can occur in these objects. And those stars die, and those objects remain dark because no further gas could accrete because the universe will reionized at some point. So the way we probe dark matter down to 10 to the 11 solar masses using galaxies as a tracer is not possible below galactic mass scales. So because those objects aren't luminous anymore, so those dark matter structures that form below those scales are dark. So we are unable to confirm whether we live in a cold dark matter or warm dark matter situation because we need to observe these lower mass scales to be able to make those differences. And the lower mass we go, the better we are able to constrain dark matter properties. So, and to this end, gravitational lensing comes to our rescue. We don't need, with gravitational lensing, we don't need these objects to be luminous. As most of you probably know, as a result of general relativity, what we have is the prediction of general relativity is that light also should be affected by energy density in a given volume of space, right? And this is what mass is. So mass bends light just like it bends trajectories of any other object. And this has been confirmed many, many times, and we see the effects of this. So what gravitational lensing means for us is that we can use this phenomenon in the sky to probe dark matter, because most of the lensing is being done by dark matter since it's the dominant matter contact in the universe. So in the background, you have a galaxy which emits some light, and the light from that galaxy reaches Earth through various paths, not a single path, but multiple paths, because of the bending caused by the foreground galaxy cluster or a galaxy. And as a result, you see this beautiful arc. So here's a real galaxy strong lens image. The reason why this is called strong lensing is as opposed to weak lensing, where the background image is only slightly perturbed, but in strong lensing, the background image is massively perturbed. You form these arcs, you form multiple images. Meanwhile, in weak lensing, you don't form multiple images, only slightly the images are a little bit distorted. So this ring that you see around this object is actually a background galaxy, the light from a background galaxy. And the center that you see is the foreground galaxy that is doing the bending. And in general, with gravitational lensing analyses, what you do is you model the foreground galaxy's light, then you subtract it from your image to be able to cleanly analyze the light from the background galaxy. On the right-hand side, you see the foreground subtracted image. Okay, so what happens is if this foreground lens has some subhalos, so you can, if we can go back to this picture, you can imagine the center mass density as the main lens. But if we live in a CDM, cold dark matter scenario, we expect a lot of these smaller perturbers, subhalos, to also exist within the halo of this bigger galaxy, right? So you can imagine in this picture that there should be a lot of these smaller objects scattered. And those smaller objects should also bend the light a little bit. Not as much as the big galaxy at the center, but observably so, a little. So these subhalos or line of sight halos, anything along the line of sight, create these perturbations in these images that we observe. And through those perturbations, we can detect them. And that's exactly what we do. So, and I'll tell you what we can learn about these by doing such. Let me pause now, because this is an important point, and I can answer questions before I go forward. Right? I guess it's clear. Okay. All right, so a little bit of math of gravitational lensing. So what you have is a source plane, and the coordinates in the source plane are usually written with y. And then you have multiple lens planes. So the reason why we call these planes is because you can assume all matter to be squished down to a 2D plane, because their z dimension, z is along the line of sight, doesn't matter, because cosmological distances are so vast, essentially their effect ends up being the same as the effect of a 2D matter density plane through some Born approximation that you calculate along the line of sight. So essentially, you have these multiple objects that you can have along the line of sight. You can have a main lens, which we show in dark black here, vertical line. And all these line of sight objects slightly bend the light coming from the source plane, and eventually it reaches us. And you can write this geometrically. So these are 2D coordinates. So this x1 is the coordinate, angular coordinate in the sky of a position that you observe. And these alpha I are all these angular deflections that are caused by these lens planes that are doing the bending. And there's a recursive lensing equation that tells you what the position is in each plane. And you can solve these systems of equations, which we do so numerically. And these angular deflections are caused by mass. In general, importantly, I should define a quantity called convergence. Convergence is simply weighted, dimensionless, weighted surface mass density at each plane. It's weighted by some distance scales that affect how efficiently lensing is being done, depending on different distance. And essentially, when I say convergence, what you should understand is surface mass density, the amount of matter in a given area in the sky. And mathematically, it's also the, you can invert this equation, you can find out that it's actually the divergence of the angular deflection field that gives you convergence. Confusing names, I apologize, but this is the field. Okay. So equations are relatively simple. So
can I ask something before
yes.
you go about the picture?
Yes.
just so that I understand that picture at the earlier slide, though.
Earlier stuff here.
Yeah, okay. My internet connection is quite bad, so. But anyway, so my question is this. There are some, shall I use this term, negative curvature points instead of positive. So I would expect this, just so that I understand this, there is this observer's plane, so to say, line of sight, where the observer sits.
Yes.
The one on the next. And there are these different focal points where there are some galaxies accumulated, so to say, and you're looking at only the 2D effect because they're so far away, blah, blah. Why are there, for instance, at the latest change, it goes up? Would you expect something like this?
No, this is just a pictorial representation.
Yeah, okay. So, okay, that I understood correctly. So the pictorial, but you wouldn't expect anything pictorial like this as well. You would expect it to be curving towards the observer plane, always, right?
Not necessarily. It can curve in any direction. If you put mass,
so the
let's
galaxies
say
can be off in Z direction.
If you put some mass here, for instance, it would bend the light in this way. So it would actually curve it up.
I was wondering about that. So the galaxies are not, so to say, accumulated on the observer's plane. Not necessarily.
There are galaxies all across the space-time volume that you see along the lens.
Thank you.
But because the size, the scale of each object is much smaller than the cosmological scale, this is not to scale, this schematic, this X distance, the horizontal distance is much, much larger than the horizontal distance between these planes are much larger than the sizes of these objects. That's why we can approximate them as being plane to the surface mass density.
Okay, I got it completely now. But I will not talk more because I don't want to take up more of your time. But thank you very much.
I should be a little bit more quickly. So how do we detect this with this gravitational imaging, which is the technique that is called using these brightness perturbations? So here's a mock image that I created using a software called Astronomy, where you can play with these things. So you put a background galaxy with some light distribution, and you put a foreground galaxy, in which case, in this case, I didn't put the light for the foreground galaxy. So for the foreground galaxy, I assume that the light has already been modeled and subtracted. So I'm only showing them, there's only the mass here, no light from the foreground galaxy that is doing the bending. So these three images that you see here are all from the background galaxy that I put in this figure. This lens is roughly 10 to the 11 solar masses doing the bending. But there's also a roughly 10 to the 9.5, 10 to the 10 solar mass subhalo that I also placed in this image. But it's very difficult to see by eye where is this small perturber. I can tell where the big galaxy is. I can tell that in the center location, there has to be some massive galaxy to produce this gravitational lens. That is very easy to tell by eye. But when you go down to 10 to the 10, 10 to the 9 solar masses, doing this by eye is not possible. But with modeling, this can be done, especially at those scales, very easily. So the way you do this is, because this is a mock case, I can show the true source and the reconstruction. In the real data situation, you can only show the reconstruction because we don't know the true source. But on the top left, you see the image, which is our data. So you generally mask the center and mask the outside because there are other foregrounds and pollution that you don't want to worry about. And you reconstruct the source distribution and the lens mass distribution simultaneously. That's a really important part. So you allow, you fit the lens with some analytic model. Usually an elliptical power law is used, which is the case here. And you allow the main lens to have that distribution, have free ellipticity, free center, and all these properties so that it can fit whatever the true, it can fit as best as it can the true mass distribution of the actual galaxy. And the source, you want to vary the source. You want to allow all these complex shapes to exist in the source plane. So what we use is these basis functions called shapelets, which are this orthogonal basis 2D functions that allow all these irregular shapes to occur, and they're controlled by different amplitudes. So in this case, you see the source reconstruction, the source, and the residual. And you also see the images. So this is our image reconstruction. So this is what our model gave us that is best guess. So this is a smooth model, meaning that in this model, I only allowed a main lens. I did not put any extra perturber. I only allowed a smooth main lens at the center, and I did not allow any small object to do some extra bit of lens. And we see that there are these extra image residuals. So that our model wasn't able to reconstruct the data really well. It wasn't able to reconstruct the data well in these points. There are large residuals that you see, which is the subtraction of data from the reconstruction in terms of noise. So this is a problem. This means our model failed. You need to add some extra components. So when you add to this model a subhalo, so the model convergence, so let me go back to smooth model first. Model convergence is the 2D surface mass density when you look at here. Now, if I add the perturber, if I add the subhalo to our model, again, the subhalo, the position of the subhalo, the mass of the subhalo, and the concentration, which tells you how dense it is and how undense it is freely varied. So all those properties are allowed to be to change however you like. And now I try to reconstruct the data from this new model, which includes the main lens and the subhalo. And here you can see the model convergence, that there's a small bump here, as opposed to the big main lens here. And now, with the addition of this extra subhalo, where the image residual is completely normal, looks completely random, which is what you expect from just image random noise. And our source residuals actually also looks better, but this is not a comparison we can make with real data. So here, this is how we detect these objects, and this is how we study them with real HSD images or James Webb images as well, by modeling it explicitly, by allowing the model parameters to change. But obviously, we have to assume some analytic forms.
Can I also ask one more question?
Yes.
So you put one additional subhalo to fit better, right?
Mm-hmm.
In this process. Who told you there is not another one?
Good question. So in general, we expect hundreds, but most of them will be small masses. Around 10 to the 9, 10 to the 10, when you calculate the number of subhalos that you expect, usually don't get more than one. So, and in a lot of these detections, generally the mass of this subhalo distribution is dominated by 1 or 2 subhalos. In this case, because this was a mock case, I created it and I modeled it myself. With real systems, the best you can do is currently with explicitly modeling like this is either putting 1 subhalo or 2, maybe 2 would, the more subhalos you put in your model, you're increasing the dimensionality of your model parameter space. And it thinks the sampling that high dimensional space becomes more and more challenging the more parameters you add. So in general, this is a big problem in lensing. If you want to detect a collection of these objects directly, you need to come up with some new methods. This direct detection would not work in that case. But people are working on machine learning techniques. People are also working on, including myself, are working on statistical methods to not detect these objects individually, but collect population statistics of them using pixel brightness. So there are ways to overcome that.
Thank you. Also, one more quick question. You said lots of things are free in this parameter, besides, for instance, the number of subhalos that you want to put and so on and so forth, right? The position is free. And how long does these take in general? Like long or not so long? I'm not too much of a...
Depends on the image size. So if your image has, let's say, 100 pixels by 100 pixels, and if you're modeling them, you're doing these ray tracing calculations. And if your source is also not very complex, the modeling takes roughly 2 to 3 days, running on 64 cores in parallel on a supercomputer.
So for me, it's long. Okay, thank you.
Yes. So that's the cost. Currently, these are a little bit computationally costly.
Thank you.
Yeah, great questions. Thank you. All right. So a bunch of challenges. True source light distribution is unknown. Lensing would be much easier if we knew what the source looked like, but unfortunately we don't. We have to model it simultaneously. There are various techniques one uses, but they all have shortcomings. And this whole thing is computationally costly due to the matrix inversion. So you have to do some linear matrix inversion to calculate the source brightness the amplitudes. And inverting 400 by 400 matrices, 10 million times is very costly. So that's why this analysis takes a long time. And some of these perturbers have very weak signal. So in general, it's very hard to quantify the selection function. What is the selection function? Is basically, it's the function that tells you what is the distribution of the objects that you expect to detect given some underlying true distribution. Because the underlying true distribution of these perturbers, you're not detecting all of them, you're detecting a biased sample of that underlying true distribution. And that bias is very hard to calculate because each gravitational lens is unique and different. And each position is different. So depending on that, you get different sensitivities. But there are people that are working on, including myself, that wrote these great machine learning papers that you can check out that try to overcome these challenges in modeling. Okay, I should be a little bit quicker. So I will pass this a little bit more quickly. So currently, we don't have very good constraints on dark matter. This is because there's only 2 substructure detections with this method so far. Because of that, our statistics are very low. We need hundreds of thousands of systems that we probe, and we need to find hundreds and thousands of these objects, smaller perturbers, using this method to make robust conclusions about dark matter. So far, all of our error bars are quite large. Here, the plot shows this F, which is the substructure mass fraction, which is the quantity that a lot of people are trying to measure. It's this fractional mass buried in substructure in a given galaxy halo. So it tells you the abundance of these smaller perturbers, basically. And the X, the cross that you see, is the cold dark matter prediction. And the contours, the blue contours, is what you see, what you get from 1 sigma errors only from lensing. And the black contours is with the flat prior, sorry, blue contours. The black contours are with a prior that is assumed with a Gaussian prior around the mass function parallel slope of the underlying dark matter halo mass function. But yeah, in general, these constraints are horrible. We are unable to rule out CDM. We're unable to rule out anything yet. But that doesn't mean it's bad news. There's a lot to come for the future, which I'll talk about in a minute. Okay. Let me tell you briefly what we did. We actually detected that one of these subhalos that were detected in one of these 2 systems, in this particular system, is actually a line of sight object, not a subhalo. There were previous studies that counted the amount of line of sight halos that you expect in these lensing systems. And for the higher redshift ones, redshift just tells you the cosmological distance. The further something is, the higher its redshift. The light that we observe from that gets redshifted more and more due to the expansion of the universe. So it's just the distance. So higher redshift objects are further away. So there's more volume in between. So we expect more of these objects to exist there. It turns out that these line of sight halos are 10 times more numerous. But in these papers that detected these substructures, they assumed that whatever object that they're detecting using this strong lensing method is a satellite of the main lens galaxy. But we broke that assumption. We said, okay, let's generalize. Let's allow the redshift of let's allow the z distance of the perturber that we're modeling to vary freely. And when you do that, you allow curl in the angular deflection field. This is an interesting mathematical point. When you only have single plane lensing, meaning that if your source gets lensed by a galaxy, only one galaxy, and reaches you on its subhalos, the angular deflections that are caused by that can be written as the gradient of a potential, which is called the lensing potential. Mathematically, this results in no curl term because the gradient of the curl of a gradient is 0, vanishes. But when you have multiplane lensing, meaning that there is a main lens and a line of sight halo, a curl emerges due to the coupling between these consecutive lens planes. And here's a visualization of that. On the right-hand side, you see the convergence of the surface mass density of the perturber that you have. What I'm doing here is I'm increasing the redshift. So I'm making the perturber more and more a line of sight perturber. When the redshift of the perturber is 0.95, the main lens redshift is 0.9. So it's really close to the main lens redshift. So it has a very small curl, has a quite large convergence. But as you increase the redshift, so you push the perturber further and further away, you realize that you see from this plot that the curl term, which is this term, becomes almost as large as the convergence, meaning that if you're detecting it using its convergence, you should also be able to see the curl and measure its redshift, which is exactly what we did. And we modeled it, and we found that the redshift of this perturber is consistent with the background redshift, and these are the 1 sigma error bars. So this object is actually not the satellite of a galaxy, but actually a line of sight object living somewhere in the background between the source and the main lens. It's not associated with the main lens at all. It's a dark object just by itself. And this has consequences, meaning it's a little bit more massive than what the previous paper has predicted. It also has consequences from the cosmology point of view. I will wrap up very quickly.
You have time.
So, do I have time? How much time do I
Yes,
have?
there are 8 minutes for the questions, but since people ask their questions during your talk, you
Okay.
can.
Great. Okay. Hey. So yeah, please keep asking questions if you have them. I'll try to wrap up. I'll try to manage my time accordingly. So line of sight halos are actually better than subhalos. If you're able to actually differentiate between a line of sight halo and a subhalo in a given strong lensing system, you're in luck, because a line of sight halo is not associated with any massive galaxy. It lives by itself in space. So it's not tidally stripped. It wasn't bombarded heavily due to the stars in that main lens heavy galaxy. So its physics is actually much simpler and much more easier to tie to dark matter models. Its number density is easier to predict, etc. So if you are able to actually detect all these substructures and perturbers in these strong lenses and measure the redshift using the method that we developed, you're able to make much more clean dark matter predictions, and that's our claim. And for the future experiment, that's the pipeline that we're trying to set up right now to make this process a little bit more streamlined, to come up with better dark matter constraints. Okay. There are also some astrophysical interests. By comparing the mass functions of this line of sight halos to the subhalos, you can also gain insights on structure formation and how these tidal stripping and baryonic physics due to the main host galaxy causes changes in these satellites compared to non-satellites, line of sight halos that live in intergalactic space. Okay. And yeah, once you start detecting 90 or so of these objects, you actually start to constrain the half-mode mass. Half-mode mass, if you remember from one of the earlier slides, is the mass scale where you start seeing a suppression in structure formation that tells you the dark matter particle mass. So using only 10 of such systems, you're not able to constrain it really well. The y-axis is the probability distribution, the posterior. But once you start getting to 100 or so detections of these objects, you start being able to rule out 0. And ruling out 0 in the half-mode mass means you ruled out cold dark matter, because cold dark matter has 0 half-mode mass. It goes all the way to as arbitrarily small masses and form structures. So yeah, that's the goal. Once you start having 100 or so detections, we will be able to make really robust conclusions. And that's in the very near future, in the next couple of years, actually. Another important property is that you actually need to distinguish interlopers, which are line of sight halos and subhalos. Otherwise, you make wrong conclusions about the substructure mass fraction. You count line of sight halos as subhalos, you think there's more substructure in a given galaxy, when in reality it's actually just line of sight objects that you thought were actually satellites of the main lens galaxy, which is not true. So that's another important aspect of this method and this analysis. Okay. So yes, in this last 5 minutes, we'll go into the most mathematical part of this presentation, which is trying to measure the density profile of these perturbers. So detecting them are great. You fit them with some analytical model and try to figure out how they look like, etc. But what we're interested in is actually their shapes, because their shapes tell us, if you remember from earlier slides, how dark matter interacts with itself. Because dark matter self-interactions, as you remember, forms cores as opposed to these cuspy structures. So we want to measure their density profiles. So I should mention this NFW profile. It's called Navarro-Frank-White profile. It's named after the people who proposed it. It's a universal dark density profile that fits cold dark matter, interactionless cold dark matter, really well. So in green line here, this is a real n-body simulation that we used. It's called ethos simulation in our paper. We didn't run the simulation. We got the results from the people who ran it, and we used it for our purposes. In green, what you see is this NFW profile, which is this analytical profile that goes like -1 and then -3 and large radii. And it has a transition radii called the scale radius. And in red, in green, you see that NFW profile. In red, what you see are the actual density profiles extracted from this particle simulation. And as you see, NFW fits it really well. And the shaded region is the Poisson noise, because these are n-body simulations that consist of individual particles. There is some shot noise. And the smaller radius you go, the shot noise increases, there are fewer particles. But it fits it really well. This NFW profile is really successful when you want to study cold dark matter and explain cold dark matter. And self-interacting dark matter starts deviating from that. But empirically, what we observed is that you can actually fit these real objects when you're modeling them in real strong lenses with only a single power law and get really good results. So it explains the data as well as fitting it within an FW. So the lensing, strong lensing cannot differentiate between an FW, which is this green curve, and the cyan curve, which is a single power law. And the question is why? So that's the thing that we derived mathematically. I will wrap up very quickly. I'll go over the math somewhat quickly to explain how this comes about. So you have some source light distribution. So let me before we go into the math, let me just quickly say, in general, we are not sensitive to the density profile in these inner regions because you start going below your image resolution, which you're not able to probe. For larger radii, what happens is the density profile of the perturber starts blending in with the main halo that you're also modeling. So you cannot tell where the perturber ends and where the main halo begins. It's like having a mountain peak and a smaller peak next to it. Where does the smaller peak end and the bigger peak begin? You cannot tell. So it's like that. But I will also mathematically explain how this comes about. So you have some source light distribution on the source plane, this source light intensity, surface brightness. Y is the source plane coordinate. And this gets lensed by a lens plane. For simplicity, I'm only assuming a single lens plane for this purpose. And this IX is what you observe in the sky. It's the intensity that you observe in each position X. And this X is the observed position, Y is the lens plane position, angular positions these are. What lensing does is it just maps ISY to IX. So IX is equal to I source, the source distribution Y. Surface brightness is conserved. You observe what you get mapped onto. And this is given by the lens equation, which just simply tells you where X gets mapped onto. But the thing is, we don't observe these images purely. We observe pixelated images. So this intensity first gets convolved by a point spread function in a telescope. Telescopes have a point spread function that if you observe the point-like source like a star, you would actually observe some distribution due to both diffraction, due to the finite aperture of the telescope, and also the chip, the detector effects. The electrons get diffused a little bit in these detector chips. So that causes a point spread function. So point sources appear. This delta is not a Dirac delta function, it's a point spread function. So this IX first gets IU first gets convolved by a point spread function, and then it gets pixelated. This is integral over some I and j pixels area. Okay, so this is what we observed, this PIJs. Great, that's our image. It's a 2D array. So now, what happens when we add a low mass perturber? You can separate the angular deflections of the main lens, which is written here as alpha m, and the angular deflection of the perturber, which is written here as alpha p. And alpha p is much, much smaller than alpha m, because alpha m is the main lens that's doing a lot of the bending, and the perturber is only doing a very small amount of bending. And then we expand this earlier equation, this new, around the place where you would get lensed only by the main lens. So when you expand that, the angular deflections of the perturber causes the position in that sky that you observe to be mapped onto a slightly different point in the source. And in that direction, the source has some gradient of brightness. So now you get mapped onto some slightly less bright or slightly more bright location due to the effect of the perturber. So the pixel brightness either increases or decreases in different locations due to the effect of the perturber. When you write it out, carry out the calculation, differences in these pixel brightnesses are written as an integral of the angular perturbations of the source, dot product with the source surface brightness gradient. And you can write the angular deflections of a perturber if it's axially symmetric as a function of this average density within some radius, which is the density profile. And when you do that, when you also discretize the equation for computability purposes, you get an equation that looks like this. You have this pixel value changes, which is our observable. You have the source surface brightness, and you have the point spread function. And you also have the average convergence of the perturber, which is the density profile of the perturber at different locations. And the important thing is this is a linear map. It maps the density profile of the perturber at various radii to the pixel value changes, which is our observable. So you can read the details in the paper. When you have a linear map that looks like this, you can actually calculate its errors by simply inverting a matrix. When you have a linear map where D is the data, L is the linear map like a matrix, and K are the model parameters that you're trying to fit for, the errors in these Ks, which is errors in our density at various radii, is simply the inversions of this A matrix, which is given by our model. When we calculate that, we basically find out the matrix elements from this equation and we calculate it. Here's the plot. So it matches our intuition. What you have in a real lensing system when you calculate this matrix, in this inner regions, the errors in density that you observe are very large. In the outer regions, the error is again very large. So there's the sweet spot between the inner region and the outer region where the errors are quite small. And that's the spot where actually are able to fit with a power law. And it turns out if you create a mock lens using the simulation with an NFW profile, which has this green curve, and then you model it with a power law, the best fit that you get from the power law matches these error bars exactly in this sweet spot, which we call the region of maximum observability. So what we're observing is actually the density profile in this region. We're measuring its power law slope and amplitude in that location. So I'll wrap up. I'm over time, I apologize. What we did is we also went back to simulations and compared what we observed from, I'll skip some of these slides. We actually made this measurement in a real system and we found out that the slope that we observed from this effective power law fitting is larger than what you expect from simulations. Problem is, it's in 2 sigma tension with CDM. It's larger than what CDM predicts, which is this green, which is this red distribution. So are we living in a non-CDM dark matter scenario? We can't say currently because this 2 sigma tension is consistent with the selection function that we expect. We expect the steeper perturbers to be detected more easily. And since this is one of the 2 systems that were ever detected in the literature using this method, the first ones that you detect, you expect them to be in the tail of this distribution that you extract from a simulation. So this is probably the selection effect. The more and more structures that we detect with this way and measure the power law slope using this method, we're able to tell whether dark matter has self-interactions or some other exotic behavior that deviates from the main cold dark matter scenario. And yeah, and that's the end of my talk. Sorry if I ran a little bit over time, around 5 minutes.
It's okay. It's okay.
Yes, so rough outline, we're trying to measure structure below 10 to the 10 solar masses because that's the place where we are able to tell between different dark matter models, because that's the place where they differ. Because any other place that they differ, we already observed. So far, it's consistent with CDM. Stroke lensing is a really good probe of such scales. It tracks the mass directly. It's a function of mass density. And direct detection is possible down to 10 to the 8 solar masses using these objects, using James Webb Space Telescope and Hubble Space Telescope. It's important to distinguish between subhalos and magnified halos. We showed that it is possible, and we've done so. And in the future, we'll build a pipeline to do that automatically. And also, we're able to measure the density profile of these objects. But the caveat is you can only observe it within some sweet spot, within some radius range. But we can calculate that radius range, which is good. So then you can use that calculation to actually compare it with simulations, which is what we've done so already. We just need more statistics. Everything is there, all the pipeline is there, all the math is there. We just need more accretion of data. Luckily, this is my last slide. Data is coming. So there's Vera Rubin Observatory, Euclid, Dark Energy Survey, etc. There's so many survey telescopes that are expected to find tens of thousands of new strong lensing systems. Currently, our catalogs have only a couple hundred strong lensing systems. So the number of systems that we'll detect will grow by a factor of 2 and 3. By an order of magnitude to 2 and 3, sorry. The problem is these survey telescopes don't have enough resolution to run good enough analysis for our purposes. So the only thing we need is follow-up observations with high resolution telescopes once you detect these systems. So once you have these follow-up observations with James Webb, which is what you see here, it's already operational. I'm already using James Webb data, which is publicly available. You can play with it if you want to. And there's extremely large telescope, which is going to be operational in the next 5 years. And yeah, we are expected to find, we're expected to have really good constraints on dark matter in the very near future with strong lensing. Thank you. Are there any questions?
All right, let me stop the recording then.